Uh, yeah, maybe we will start. We are happy to have Pratik Nanti, and he will be talking about quantum chaos and complexity in the many-body systems and holography. Yeah, Pratik.
Okay, thank you. Thank you very much for giving me the opportunity to talk about my work. So today I'm going to talk about some notions of quantum chaos and complexity in different diverse systems, including these many-body systems and holography. However, these notions, chaos, complexity, are very broad. So I will narrow down in some definitions, and I will talk about my work in those aspects. So the motivation is follows. The recent years, for example, the ideas of quantum information has been a revolution in ideas in condensed matter and idea safety. For example, in holography, examples are like quantum information ideas are like quantum circuits, how the circuit quantum gate circuits plays an important role in understanding, for example, the late time physics of the dual picture in the black holes. And also in the many body systems, such as thermalization phenomena and operator growth, these kind of phenomena also plays a significant role in developing our understanding about physics. And especially in this context, one of the key quantities maybe I would say three key quantities played an important role. One is entanglement, which I'm not going to talk about in this talk, but the other notions such as complexity and the quantum chaos, these is two are the very important like I would say like tools to understand this kind of physics. However, there is no good definition of a complexity for many body systems and holography. Recent years, there are a lot of different notions of definitions. So I will give you one definition and try to motivate whether this definition is actually, how this definition is actually good compared to the other definitions and how that teaches. So first of all, there's a very beginners for non-physicists, for example, how do we encounter chaos in everyday form? We all have some intuitive notions of chaos because, for example, if you go out of institute, you will maybe encounter similar like this. And this is the classic example of, for example, in Indian street, we call system is chaotic. However, and we usually associated different terminologies, for example, randomness, disorder, unpredictable, many things. However, these are like generic term. We need to more a physicist term. Even in your cafeteria, in a cafe, you can also encounter this kind of chaotic phenomena. For example, if you mix milk and coffee together and this kind of mixing, and it thermalizes, and this is also the fundamental principles of chaos. In fact, most of the physical phenomena nature is in chaotic. For example, weather mechanism. In context of quantum gravity, black holes are also known to be maximally chaotic, maximally scrambled, chaotic. So it's an interest to develop a theoretical framework to explain what is the underlying mechanism of this kind of physical phenomena, because it's a vast physical phenomena. And another application of this thing is that you can have this phenomena this kind of notion, this kind of expansion will guide us to develop efficient quantum simulation if you want to develop a quantum algorithm which you want to simulate the nature. So we need a better understanding of this kind of quantum phenomenon. Okay, so I will first describe back to the physicist definition. I will first describe the classical chaos, and then I will describe what is quantum chaos in terms of a particular notion, what is called operator growth. I will describe what is operator growth. And then I will define a notion of complexity in both an operator space and a state space in terms of a notion of Krylov space, which I have been working on past 2 years. And these are the references which will be discussed in this talk, more or less. And I'll give some examples and give some future goals. And the main results, more or less, are given in our review article, which appeared this year. And you can check the details if all the details. In particular, I will highlight these two colors. For example, this blue colors is the key formulas definitions, and also the red colors are basically the key takeaways, results, whatever I'm going to. So whenever you see the red colors, that is basically the key message. So I outline what is the key message of the work. Okay, so we'll start with the classical chaos, where it is very basically well defined, very well defined, and it described in terms of how sensitive my future predictions in terms of my how I change the initial conditions. For example, you can see in terms of this classical billiard. If it starts with this particle, can you see my cursor here?
You can see.
Yes. Okay, great. So if suppose I started some particle from here, and I project the particle in the billiard, and it follows a motion like this. And suppose I change some infinitesimal this particle trajectory. So in the very infinitesimally, at later time, you can see this, it goes completely out of the order from the initial the other trajectory. So changing some initial conditions will give a very drastic changes in the future. So in a phase space, we can write in terms of like into a coordinate, position and momentum coordinate. This is basically the change of the initial condition, and I get a final outcome. And it grows exponentially. The trajectory grows exponentially. And usually written in terms of the classical Poisson bracket. However, in quantum mechanics, we first approach a semi-classical approach. So what we do is we take a Poisson bracket, we elevate to the commutator. So that's how we elevate to the commutator. And this is the way we define a notion of OTOP. It's called out of time order correlator, which is basically a square commutator between these two operators. For example, we can, instead of position momentum operator, when we talk about quantum mechanics, we can talk about any generic operator, not necessarily any position and momentum. So a operator is evolved usually in the Heisenberg picture in quantum mechanics. So we define the time evolved operator as a Heisenberg evolution, and taken, for example, initial operator, and describe how the OTOP. This angle bracket can be defined it depends how we define whether it define in a infinite temperature or in a thermal ensemble or in a zero temperature. So it can be either trace, or can be any thermal product, or can be any just a state. For example, if we compare any zero temperature limit. So this exponential growth of OTOC can be is usually known to be a signature of quantum chaos in semi-classical systems if it grows exponentially. And this lambda L is a different than lambda CL. Lambda CL is a classical Lyapunov exponent, but lambda L is a quantum Lyapunov exponent. Is a signature of chaos in semi-classical systems.
Hi, Pratik. So what do you mean by exponential growth of OTOC?
So exponential growth of OTOC, for example, if you compute this operator at early time, because this is a time evolution, this depends on the time. So this quantity will show an exponential growth in the early time region.
So what ensures that there is only one, always positive exponents? What ensures that? You are assuming that it grows exponentially with time with some positive exponent, but what guarantees that there is a positive exponent, or what guarantees that there is only one positive exponent?
Yes, yeah. So okay, so there's no guarantee. There is no guarantee. So I'm simplifying many statements. So there could be different Lyapunov exponents. Sometimes we take the maximal of all the different Lyapunov exponents, different OTOP, and we call that's our OTOP. So it's not a guarantee. But
so what is the most general criteria in these kind of situations in a complicated one? Suppose you don't have only one positive Lyapunov exponent, but a multitude of positive Lyapunov exponents. And what is the criteria for quantum chaos? So how do you quantify that?
So if you have a multiple Lyapunov exponent, you can define that the maximum of this all the Lyapunov exponent is the quantum Lyapunov exponent. That is one of the definition is used sometimes used in literature. So if you have different.
Where is the information of all the other positive Lyapunov exponents going? Like
yeah,
they
so
also
as I'm going to say, this is not a very good proper well definition. Yeah, so there's many
are
things.
Are there any other generalized definitions for these systems?
Like in terms of OTOCs?
Or in terms of some other quantities which characterize chaotic systems much more better?
Yeah, so that's what I'm going to discuss next. Okay. So I will say that this OTOC is not a very good quantity. So there are better quantities that I can describe, and this Lyapunov exponent, the maximal Lyapunov exponent, one Lyapunov exponent is basically chooses from this growth of the other quantity that I'm going to define.
Okay.
Yeah. So the OTOC is one of the very crude way to go to semi-classical and then to quantum. Okay. Yeah. Please ask any questions if you have. So interrupt. Yeah. Interrupt.
Sorry, can you hear me?
Yeah. Sure.
Yeah. So small clarification about this t, the time t. It should not be very large so that it crosses this. I mean, the Poincare recurrence, right? It should be.
Yes. Yeah.
It should be
Right.
somewhere in
So
between,
I
right?
can say it's an early time.
Yeah.
Early time exponential growth. You will say early time exponential growth. Yeah. Okay. Okay. So however, we should keep in mind the origin of OTOC. The definition is a purely semi-classical, and it's well defined for system with large degrees of freedom. So normally in the black hole context, when all the holographic context is a large n systems, people usually compute the OTOC, and that's how the black holes and scrambling phenomena are there. However, if you have a small number of degrees of freedom, what is in a true quantum systems, which may have does not have any semi-classical, for example, in spin chains. Okay. How can we define the OTOC? We can just define OTOC. There is no problem of defining the OTOC, but you can show that in spin half chaotic spin chain does not exhibit the exponential growth of OTOC, even it's in chaotic systems.
Hey, Pratik, when you
Yes.
tell it is a chaotic system, the spin half, how do you know that it is chaotic?
Okay, so this chaotic I am defining in terms of a static spectrum in the level statics definition, like how the eigenvalues repulsion.
So you take the Hamiltonian, and then what does it follow? Which random matrix theory does it belong to?
So I have an Hamiltonian. There are different symmetry I can have in the Hamiltonian. Time universal symmetry,
Yeah, sure.
Yeah. So depending on the time reversal and other symmetry classes, this will follow some Gaussian orthogonal ensemble, interior ensemble, or symplectic ensemble.
Yeah, sure. But I wanted to know what specific example are you mentioning here when you mention this is a very generic.
Yes, I will show an example.
Because this statement is not always true. The spin half chaotic spin chains. Means there should be some things which you have in mind, which is not clear from the statement.
Yeah, so what I in mind is that if you take spin half chaotic systems like an Ising, I should mention that, for example, a specific class of spin chains called mixed field Ising models. Those systems will not exhibit chaotic exponential growth of OTOC. But if you increase the spin in half, one, and spin j, and you take j tends to infinite limit, so it's basically a semi-classical envelope, then you can see it's an exponential growth. But within the spin half only, which is a truly quantum system, there is no problem defining spin half, but you will not see the exponential growth of OTOCs.
And this system is different because the spin half chain is a quantum system. It doesn't have any chaotic properties. What you're telling is you go to higher spin representations and then you have a then it is a very different theory than this one.
Yes, so I'm saying the spin half chaotic spin chains, so a class of chaotic spin chains, for example, I'm going to show an example there later. It's called mixed field Ising model, where you have like a transverse and longitudinal magnetic field.
Then those are different. Those are specific conditions where you impose chaoticity. But this statement is very generic, so it doesn't tell you anything.
Okay. I see what you mean. Yeah. So I should say there are classes of spin chains, chaotic spin chains, which do not exhibit exponential growth. Not all. Yeah. Sure.
There you don't even go to large J limit. You can do it for spin half systems also by taking different couplings along the transverse and longitudinal directions, right?
So large J, I mean the spin
yeah,
half.
sure. But I'm telling that even in transverse Ising model, transverse field Ising, you do not need to go to beyond spin half. You will always see chaoticity even in the spin half systems.
I can see the chaoticity in spin-off system. For example, if I have a Hamiltonian and I can diagonalize the Hamiltonian, get the eigenvalues, I can see how the eigenvalue repulsion, for example. Even spin-half, I can completely see the chaotic nature of the spin set. So this way I know that our system is chaotic, but this is a static spectrum, Hamiltonian only. Now I see the dynamics because of the time here. So it's a dynamic. So the static chaotic spectrum and dynamic manifestations from chaos, they do not always agree.
Okay, please go ahead.
Yeah. So can you remedy this formulation and formulate a generic notion of operator growth in a truly quantum systems? So like we'll attempt to develop a notion of operator growth through this Krylov space, and we want to refine our understanding of quantum chaos, because I will show that this Krylov space has some intuitive properties and more also a kind of better in the sense of OTOCs, and they can capture what OTOC cannot and give an idea. So I share the key contributions that in the talk that I'm going to have. We provided a first mathematical constraint, and I'm going to explain these 3 points in my talk. Is that how the operator growth hypothesis in Krylov space give a mathematical constraint, and then I will also show that how we can generalize this notion to open quantum systems, because these open quantum systems is quite relevant in the realistic systems. And then I will discuss how this Krylov formalism, describing in terms of a quantum states, give a non-perturbative form of something called Langevin coefficient, which is related to the double scale SYK model and some holographic model in J gravity. Okay, so first I will go slowly and describe what is operator growth. The question we want to address: how does a local perturbation spread or scramble into a system? Suppose I have a time Hamiltonian, time independent Hamiltonian. We can also formulate everything in terms of as a time dependent, but for the moment I consider a time independent Hamiltonian and an operator which O0, which is not a conserved quantity. Otherwise there's no growth. So, and this is my Heisenberg time evolution. And I can expand this Heisenberg time evolution in terms of nested commutators. So I can, nested commutator means that each individual commutator, they increasingly commute with the Hamiltonian. They can commute with the Hamiltonian. For example, I can take a mixed field Ising model. This is one of the examples that I was telling before. This Ising model, and I can take an initial operator, which is Pauli spin sigma z in a lattice site 1. 1 means that I am in the site 1. So I can try to compute the nested commutators, how this looks like. So you can see that whenever, as I keep on growing the nested computing the nested commutators, the support of the operator, which is supported on the first site, it increasingly grows. It becomes a second site operator, and then becomes a third, 3 site operators. So in the sense, the real space, the operator grows. How do we capture this notion of operator growth? That is one of the questions. Okay. So I can write the time evolution, the OT, in terms of the nested commutators. And I will define a Liouvillean superoperator, which is basically acts on some operator, and its definition is basically it commutes them. It's a definition that it's a commutator of the Hamiltonian, which means I can rewrite my time evolution in terms of these nested commutators in terms of the Liouvillean acting on operators. Each of the operators, I am starting with some initial operator. I am acting on Liouvillean n times. I am getting, which is basically the n times means the n nested commutators, and this is basically rewriting this thing to this language exponential of ILT again. Okay. However, this basis, this basis, same basis, they are not orthogonal with respect to some inner product that I'm going to define. This is some notion of Frobenius inner product that people know. And this is basically the usually called infinite temperature inner product, which is basically the trace. In this case, you can show from the previous example, if you take there's a nested commutator, you can show that, for example, one of the nested commutators, they are not zero. This orthonormality breaks down. So the basis is not an orthogonal basis. I am expanded in time evolution is not an orthonormal basis. So how do we go expand it on orthonormal basis? But usually like to a complete orthonormal basis set for the evolution.
Hey, Pratik, what is the constraint on the sum over n that you have put? Can you have a very large delocalized operator? Because that violates the locality principle in quantum field theory. So how do you define quantum field theory in this?
No, so here in the first case, I have defined a local perturbation, local operator. So at the moment I'm keeping this for the local.
That is true, but you are now telling that you have a large spread of the operator throughout all lattice sites. So there should be some constraint. So where does this constraint come from?
Which constraint?
It cannot be the final.
It's
Your
like,
O of t should not be a very non-local operator. It should not spread across the whole lattice, whatever you have. Then
it can spread over the
how
whole
do you
lattice.
define? Then how do you define your quantum field theory in that sense?
So quantum field theory, usually we define in terms of like in correlation functions, right? 2-point function. So the whole formalism can be written in terms of a 2-point function. So here it's a local spin change. I have a local operator at my sites, and it grows in the different sites. In the quantum field theory, the operator is already a non-local operator, right? So
it's non-local, but there are constraints on the non-locality. If you cannot have any arbitrary non-local operators because it violates different principles in quantum field theory. That's what the discussion in Weinberg goes like. So there are constraints on that. So I just wanted to know what are the constraints that you have in this system of operators when you do
operator,
this kind of expansion.
O0, the O0 operator, right?
Yeah.
So yeah, so I'm defining at this moment that O0 is my local operator.
No, I'm talking about OT, O of t. What are the constraints?
O of t.
Yeah.
Yeah. So O of t can be highly non-local. It's usually non-local operator. It's non-local, and at maximal, it can have the support of the full system. If I have an n-site system,
how does this norm of these operators they behave at large distances or large separations?
Like this, for example, this kind of operator, right? Nested
Even
commutator.
then, there is a specific dependence on the distance. I want to know what is the dependence on that.
You mean the distance on the lattice sides, right?
Yes.
Yeah. So usually this distance are calculated in terms of how this light cone structure and the butterfly velocities, like how it can be a linear or non-linear, the velocity of how this operator grows. That is like, suppose I have a site here and the operator grows and it commutes with the here. So if there is a finite speed the operator can propagate. So, and that speed is controlled by this butterfly velocity and the light cone structure of the operator. But when they have a spatial separation, but here there is no spatial separation. It's at the same time, it's only a temporal evolution.
No, I understand, but it is a superposition of operators which are spread across the whole lattice. So if you take a number of terms, so my question was, how does it not violate the locality principles of quantum field theory?
So this is not a quantum field theory here. It's just a spin chains, right?
That is fine. You can always write field theory out of it.
Yeah, it's like a lattice spin chains. I have an operator propagation.
No, you are written it in a quantum mechanical sense. So is it true also for quantum field theory or not? That's what I want to understand.
So in quantum field theory, you cannot directly construct this basis because it will not make sense. This basis, this kind of nested commutators will not make sense. So you need to project your operator in some energy basis, and it's a microcanonical window, and that microcanonical window you can define your this kind of nested commutators, but not in generally.
Okay, please go ahead. If I have questions, I will ask you later. Yeah.
Sure. Yeah, thanks for the questions. So currently this is like a simple spin chains, and I'm just playing with the spin chain with some initial local perturbation and see how this perturbation can spread, and at most it can spread the full system. That is the, and OT will be highly non-local in that sense at late time. So our task is to find an orthonormal basis set so that I can expand this time evolution operator. So if I have not orthonormal basis state, how do I go to an orthonormal basis state? Is basically what we call as a Gram-Schmidt orthogonal procedure. And this context, this procedure is known as Langdor's algorithm. So I'll have as input H and initial operator, and I implement the Langdor's algorithm, which is basically the Gram-Schmidt orthogolation, and I get some basis which is orthonormal basis, and this basis I call Krylov basis. So that this basis is orthonormal in the definition of the inner product that I defined. And during this Gram-Schmidt procedure, there will be also if we remember, then this Gram-Schmidt procedure is basically an algorithm which is normalizing in every step, so you get some normalization constant. So this is Langlois coefficients are some normalization constant out of Gram-Schmidt procedure. So when I implement this Gram-Schmidt procedure Langlois algorithm, I get two outputs. One is the orthonormal basis states and some normalization coefficients, Langlois coefficients. We should keep in mind that both this Krylov basis and the Langlois coefficients, it depends on the Hamiltonian and also on the initial operator. If we choose a different set of operators, I'll get a different set of Langlois coefficients. I will come back to this point later. Okay. So I can write the time evolution in terms of a Krylov basis. So like this OT in terms of this ON. I'm going to show that this basis of ON is not Hermitian. So the product I to the power n ON is an Hermitian operator. So these functions are kind of real functions. Okay. So this time evolution I can write in terms of a Krylov basis, but here I have given an upper index dk, which is the dimension called Krylov dimension. Is basically this dk is a number where my Langlois iteration stops, because it's a Gram-Schmidt procedure, so it stops at some process. So dk dictates where this process stops. That means I have only dk number of basis vectors in my Hamiltonian, not the full operator space. And usually this dk is less than the operator dimension. So it's a numerical advantage. First of all, not too much numerical advantage, but some little bit of numerical advantage when you want to compute, when you map the Krylov space. What it means that to see the operator evolution, we do not need to know the full evolution, full operator space. We can focus on what is subsector of the Krylov space, and that encodes the essential physics. And that is basically what is Krylov space, and dictates the dimension of that space.
Pratik, what is this dimension of curly H? What do you mean by that?
This is the Hamiltonian dimension of the Hamiltonian.
So how do you define this curly Hamiltonian? It was not defined earlier. What is this?
So it is the dimension of, I should say, it's an H, because like for example, it's an n cross n Hamiltonian matrix is then basically n dimension. Yeah.
Okay.
Yeah. So that is how n cross n matrix, or even in the operator case, it's an qubits case. So n will be 2 to the power. The dimension will be 2 to the power n. Yeah, in that sense. So I can write in terms of in Krylov basis, and this function is phi n. These are known as a Krylov basis of a function. Is basically the probability amplitude, or the amplitude of the operator. And since this is an unitary evolution, they are constrained, so they are sum up to 1, up to the dimension. Okay. And interestingly, this phi n satisfies, or a function satisfies a very simple equation. For example, if I take the operator and I write in a Krylov basis, and I can write the Heisenberg evolution, which is basically the Heisenberg evolution, and I can rewrite this thing into a 3-term recurrence relation. And these bn's are basically the same Langlois coefficients. So what it means that I have mapped my full time evolution, complicated time evolution, into a one-dimensional chain, where these bn's are basically the hopping amplitude from one side to another side, and phi n as like the wave packets from each side. So what it means is that whatever complicated Hamiltonian operator growth picture I have, I can always write into this kind of one-dimensional chain, and this bn and phi n are bn's, and phi n's are both comes from the Langlois algorithm. So it's basically becomes a simple one-dimensional problem with an initial condition. The Liouvillean that I defined initially, which is basically the commutator with the Hamiltonian, I can write in terms of in this Krylov basis, and this takes a simple tridiagonal form, which is basically the Langlois coefficients in this tridiagonal form, all energy. So that was what usually people call the tridiagonalization. So I have mapped and problems into tridiagonalization procedure. And this chain is known as Krylov chain. And the Krylov now we define what is since the particle hopping problem in this chain, I define what is my average position in this chain. So this is the quantity, the average position. This is the probability amplitude. I am defining an average position of this chain. And what we defined is Krylov growth or Krylov complexity. And you can also define, for example, the higher moments, because it's just a probability amplitude. So this is just a position So you can also define the variance, the other moments, higher moments, stimulants, many things from this wave function. But this is the crudest approximation, like the least, the quantity that have a least information, the Krylov complexity, simplest quantity of the position. And I'm going to focus how this quantity behaves in different systems. Yeah. You can also analogously formulate the same thing in the evolution of the quantum states instead of operators. For example, if you start with the initial state, which is not an eigenstate of the Hamiltonian, and in the state, you can represent in terms of a Krylov basis, but the basis is formed by acting on the Hamiltonian. Instead of a Liouvillean, here is the Hamiltonian is here, the picture. And the Langdon algorithm in the Krylov basis, you can start with some initial state, and you reiterate the same procedure you did in the operator space, and you can write in terms of a Krylov basis. And this Hamiltonian is written in terms of a tridiagonal Hamiltonian. But you notice there is an additional terms, diagonal terms here, which is AN, is for the quantum state evolution, which does not appear for the Hamilton, for the Liouville evolution because of the hermiticity condition of the operator.
Sorry, Pratik, just to clarify. So this
Yes.
complexity does not depend on these coefficients B's, is it? It's just
No,
depends
it depends
on
on the B. Yes, it depends because you can solve this phi n from this equation.
okay, I
And
see.
this is basically,
Okay.
so it depends on the
Solves.
B.
Fine.
Yes.
Sorry, thanks.
So it depends on the B, and in the previously, the B depends also on the ON and H, O0 and H. So the all
Okay.
Krylov complexity depends on how your initial operator is and how your Hamiltonian is.
Okay, thank you.
So it's a complexity of the operator O0 with respect to the Hamiltonian.
Right, thanks.
Yes. It's a basically operator dependent statement. So I will you can ask why. So every different operator, it has a different complexity, right? It's true. There's and that's what you expect. Different operators should exhibit a different notion of complexity. But you can also say that the basis, my basis, the Krylov basis also changes every time if I do a different operator. Yes, that's a disadvantage, but it will show that disadvantage is good. It's a good thing in few slides. Okay, so I'll come back to this, and you can also define the notion of state complexity in this quantum state evolution, like in mapping to one-dimensional chain, and then solve the Krylov wave functions and Krylov country. And usually in the state version, it is called spread complexity. It basically dictates how your quantum state spreads in your full Hilbert space. Okay, so that's what is called spread complexity. I will come back to this state picture at the later end. Now we focus on the operator complexity.
Can I?
So this is the famous
interrupt?
hypothesis that was posed in 2019, 18, is that
After
for any chaotic
Huh?
systems.
Huh.
Sorry.
Can I ask? No.
Yeah, sure.
Can I just ask one thing? Sorry. In the previous one,
Here.
where you defined that Krylov complexity.
Hmm.
So is there a notion that phi n is most distant from phi 0, or is there no such thing?
No, there is. So if you say the distance there, then we need to define what is the distance, right? So yeah. So
this definition makes sense to me if somehow phi n is, or the phi d, whatever the last state is the most distant from what you started out with. And this is telling you how it spreads and something like that.
Yes.
Is there such a notion, or are they all democratic in terms of?
No, you cannot really define the kind of
because this
distance,
is subject to some reordering of the phi n, right? I mean, I could just make, like what you call phi d, the last state. I can put it as phi 1 or something, and then it gets a very small weight.
No, this n is not a reordering. It's a Langdon iteration. You can see this Langdon algorithm.
So it is very specific, and that
yes,
tells you a very definite way of progressing. I guess.
Yeah, it's an order. It's not a disorder. So Langdon's coefficient is bn is b1, b2, b3, b, and this is a specifically growth.
Yeah.
So
okay.
It's not. You can reorder.
Okay.
So, but one thing you can show is that how at particular time. For example, you can take t equal to, let's say, 10 at time, and you can try to see how different index behaves, and they have a very different profile that you can show. But it's not like any distance you can compute between phi n or phi 0.
Okay.
Yeah. But
Can I ask?
you can of course compute, for example, an overlap between phi 0 and phi n, for example, right? That is also possible if you define this inner product as my distance, but it's a very crude distance. There is no notion of proper distance.
If they're orthonormal, that would be 0, right?
Yes, yeah.
Normal,
So orthonormal speed is not generally orthonormal.
So this complexity K of t, it is dependent upon the choice of your basis, right?
Is dependent on the choice of my operator and Hamiltonian,
Yes.
which defines the
Yes.
basis.
Yeah. So
Yes.
if you choose a different basis through this Gram-Schmidt orthogonalization procedure, you will get a different value of K of t, right?
So in this way, I can get an unique basis.
Yeah, but if because Gram-Schmidt doesn't provide you always, this is extension of your basis from H and theta 0 to a full basis, right? And that extension is not always fixed.
Sorry, I didn't understand your question. You have a different basis. So
Yes,
I have a basis.
But if you choose a different orthonormal basis, either for the operators or for the states, you are supposed to get a different value of this complexity, right?
Okay. Yeah. You can, in the next slide, I will show that you can choose a different basis. For example, Pauli basis, generalized Pauli basis, right? Something that you have in mind.
Yes.
Yeah.
Yes.
Yeah. I will show. Just one slide. I will show you can actually define the notion of complexity in that basis also, and which is different than here.
Okay.
Yes. Yeah. Just give me two more slides. I'll go.
Sorry, Pratik.
Yeah.
So this Langko's algorithm that you are saying,
yes,
you mentioned, what is the basis of that? What is that algorithm?
Okay, so algorithm is basically I start with an initial operator, so O0, and I act on my Liouvillean. This means the commutator of the Hamiltonian, and that is my, for example, an operator which is I define O1, and I can compute whether this O0 and O1 they are orthonormal. Usually they're orthonormal because of definition, but now I can define Liouvillean which act twice to the initial operator. But one you can see that this twice of the Liouvillean, just for example here, they are not orthonormal. So what will I do? I subtract the first vector.
I see. So the usual Gram.
Yeah, usual Gram-Schmidt. Subtract the first vector, and then I put the orthonormality condition. But this vector is not an orthonormal. It's an orthogonal, but not orthonormal. So I would normalize that vector, and I get a coefficient, and that is my coefficient is P1.
I see. So through this inner product, the Hamiltonian is entering the story, right?
Yes. Yeah, right. Exactly.
Okay.
So I repeat these things, each individual, I get a set of basis O0 and B. Yeah.
So Pratik, your claim is that given the Hamiltonian and O0, this basis is unique, this ON.
Yes, right. Yes.
Okay. Thanks.
Yes.
And Pratik, do you only do Gram-Schmidt or orthogonalization, or you also have to do conjugate gradient? Because both of them are required in Langko's.
Yeah. So I'm saying kind of Gram-Schmidt procedure, but there are some subtleties involved there, including. But
you have to
usual
find out the
formalism,
basis taking into account orthogonality conditions. So just Gram-Schmidt doesn't help you. When you go to larger and larger operator space, you have lots of paths in which you have to see which path is the most steepest descent path. You have to go to the minima of that. Otherwise, this algorithm will never stop. It will get stuck and it will get infinitely running on forever.
So it will run because if there's bases are not orthonormal, so it will become orthonormal if we, for example, in the third stage, I need to subtract first two, not only the two. So nth stage, I have to subtract all the n minus one basis. So if you do this algorithm, these things, then it will become an orthonormal basis.
Okay.
Yeah, I have a small question. So when you do standard Lanchos, so we terminate at certain point. So because we assume that the Hilbert space, it not explore Hilbert space. In that case, Lanchos is helpful. But here you are working in the operator. So you have already like the power dimension. Let's say spin hub. The dimension of this Krylov space is 2 to the power L square or 2 to the power 2L. So if you are taking the full, 2 to the power 2L for spin hub. So if you are not terminating at certain point, then for large system size, these Lanchos will not helpful, right? So So what is like the Lanchas is helpful when you are finite, something you are terminating. So if you're taking the full Krylov space to the 12, so how is that
Right.
helpful? Even numerically, like.
Okay, so for example, if you, as you said, that the 2 to the power 12, or maybe that is my full operator space. It's not the Krylov space. So the Krylov space dimension is maximally bounded by this quantity, which is not very less than 2 to the power 12.
That is 2 to the power 12 minus minus 12 plus 1, but it is the order of 2 to the power 12, right?
Yes, 2 to the power 12. But most of the cases, you can see that this thing truncates much fast, much earlier. It doesn't go to this value.
Yeah. So yeah. So what is the condition? Like, is it always that we can truncate at some iterations, or because if you're not truncating at some iteration, then there is no point 2 to the power 12. So
yes.
it's very.
So if you want to see this early time exponential growth behavior, you can truncate up to some, let's say, up to 100 iteration. That is fine. If you want to see the very late time physics, then which is where the finite dimension of your Hilbert space matters, operator space matters, then you need to go to the higher. I mean, you need to go to the full later. I mean, the very late time, which means that you need to go explore the full Krylov space. But Krylov space, if you choose a very, very typical operator, it is much less than your full operator space. So numerically, it is better, one sense. And the physics that you want to extract, that, for example, I'm going to show here, that only requires maybe 30 or 40 iteration. Is fine, is exact. Yeah, so it's very efficient. You do not need to diagonalize the full Hamiltonian or run the Krylov algorithm to complete the end of the Krylov basis. Only up to certain iteration will give you the physics. Okay, so yeah, any question? Yeah, I'm going to show an example. So I'm basically waiting to come to the example where I can explain.
Just a continuation on that. I mean, that depends on what kind of Hamiltonian you have. Like usually you cannot truncate. If let's say you have a gapless Hamiltonian, you cannot truncate the Langchos very quickly. But if you have a nice gapped Hamiltonian, then you can truncate in like 30 iterations or something. But that's a property of the Hamiltonian also, along with the...
Right. Properties of Hamiltonian, also the properties of operator as well. It depends.
Yeah, so I mean, those depends on the system. So I mean, there's no generic statement that one can make that this will always work in 30 iterations.
Yeah, I'm saying I do not need to explore the full Krylov space. I can trunk it at some particular n, and I can extract some particular physics, and I show how to do that.
Right, but that's not guaranteed to capture the full physics that you would get by running the Langchos all the way. That is not guaranteed.
Yeah, full physics. Yes, that's true. So what I'm saying is I'm trying to get this exponential growth, the chaotic nature. That will be useful only in the very early Langchos coefficients, not the full iteration. If you want to see how the operator...
That would always be captured for any generic system, or I mean, that cannot be, right? It has to be some some constraint on the system.
No, that's the hypothesis that I'm going to say that it's a very generic statement.
Okay, thank you.
It's a very generic statement. Yeah. So any question? Okay. So the hypothesis, that is one of the statement that I'm going to say, and the picture is taken from this in paper, that say that any chaotic systems, chaotic in the sense that the spectrum follows the level repulsion, and in the thermodynamic limit, that means you have taken very infinite long systems. The Langchos coefficients for any local operators, they grow linearly, and this is the maximal growth possible. So the Bn, they grow linearly with an index n. So B1 and Bn, this is a linear growth. And you can see that, for example, this is a typical linear growth. And you can, you can see from up to n equals to 20 or 20 iterations, you can see that this is a very nice linear growth feature. Integrable, and since Bn grows linearly, you can solve this equation because it's a Bn and a phi n are independent, and you can solve the Krylov complexity after solving these equations. So I should say that this equation in some cases are analytically solvable and not analytically solvable in many cases. So one need to do numerically solve this equation, but it's a Schrodinger equation, so solving is quite easy as well. And this, with phi n, you can define the Krylov complexity. So when Bn grows linearly, and this symbol dictates asymptotically. That means it's an infinite chain. The Krylov complexity grows exponentially with an coefficients to alpha, which is basically comes from this alpha. Integrable systems usually show sublinear growth, like this kind of, which is not a linear growth, and which is some different notion. And Krylov complexity shows like a power law growth. So it's a very distinct feature how my complexity shows a growth in exponential or power law. And this is defined in terms of thermodynamic limit. So it's assuming the system size is infinite. But if you have a finite size system, even in the finite size system, you can get a region where you can define your asymptotic limit.
Sorry, Pratik, these are for 1 plus 1 dimensional quantum systems, or this statement? Or
yeah, this is like I would say 0 plus 1 dimension. It's like all temporal evolution, no spatial.
0 plus 1. I see. Okay.
Yeah, you
Okay,
can fix your space as well. If you can define 1 plus 1, you can fix your space and do the same thing.
Okay.
Yeah. So for example, SYK is a chaotic system, so you can see the linear growth here, and XX model, for example, integrable or these models, you can show a sublinear growth. And some models which are free model, you can map to a free fermionic model, and you can see that Bn does not even grow. It's like order one number. So you can clearly distinguish this feature from different model. Okay. So I give 2 examples. For example, this is example. This is one of the examples that I wanted to come as quickly. Is that I have a spin half mixed field Ising model, which is like Ising, that one that I have shown before. And this is one of the region is called the chaotic regime, especially in the level repulsion. This is the Hamiltonian shows the chaotic regime. And this is the numerical analysis that I can perform. Here is the system sizes. And I can show that even up to the L equals to 30, I can see a clear linear growth. And this saturation comes because of my system size is finite. So system L equals to n is a finite size system, and ultimately it will fluctuate and ultimately go to 0 at some point. And that's the Krylov dimension. But we do not need those values. We can just see the linear growth, which I increase the system sizes, and I can clearly see the linear growth appears here. And this L equals to 12 size, system size, or 11 system size, I can show a clearly exponential growth of Krylov complexity. But if you do the OTOC in this system, you will not see an exponential growth, even if it's chaotic systems. So, and getting this, seeing this kind of exponential growth for such a small size systems is remarkable, because usually in other methods, you cannot cannot deduct this kind of dynamically, this kind of behavior. This is a very nice feature. What is this Langdus coefficient dictate? Another example is the SYK model, where you can do exact analytical calculations. For example, this SYK model, I have not shown the computations, but you can show that Bn they grow linear, and this is the linear form. And the large n, index n, this is basically linear growth. And you can also show that Krylov complexity with this Bn, it grows an exponential growth. However, here you can also see that Krylov complexity and OTOC both show exponential growth. So this is good. But in a spin chain, you can clearly see that Krylov complexity has a practical advantage. The Krylov methods, and not Krylov methods, is a practical advantage over the usual OTOC methods. Yeah. And given a system, given an operator, you can run on the many operator. And one thing I didn't mention here is that what is this alpha? This alpha is a order 1 coefficient, which which depends on your Hamiltonian and the different an initial operator. So suppose you choose another operator, Bn will show a different growth. Sorry, different growth, but it should be again linear. It cannot be sublinear. So that's the hypothesis says whatever operator you choose, as long as it's a local, the Bn will always show linear growth, and this alpha is a coefficient that will depend on different operators. But that is not the concern of the hypothesis. Say that Bn will always grow linearly.
So this example, this example 1, if you can calculate the level spacing repulsion.
Yes.
So what does it give you in that case?
It's chaotic. Yes, yeah, is a Lewis distribution.
So it is captured. It is quantum It has quantum chaos, but it is not evident in the OTOCs. That's what your
Yes,
statement
yeah,
is.
right. In static spectrum, you can, but in dynamically to capture this chaos is a very difficult. Static spectrum, L equals to 12, it's simple, it's easy. You diagonalize it, do it. But dynamically, it's very difficult to capture the chaotic. And this is one of the way that gives a efficient way to do this.
Onto a spectral form factor. Yeah. So what about the spectral form factor? Have people looked into the spectral form factor of this mixed field Ising?
Yes, yeah. This model you can show the clear RAM, for example.
Okay, there also it shows chaos, or
yeah, but those are static spectra. The spectral form factor, the thing that you define is not necessarily a time; it's a parameter, right?
You can define it generically in terms of both S and T, and then you have time as well as the static parameter S. But you're saying with just S alone, it just the static alone shows the chaos.
Yes, it
okay.
does.
Level spacing anyways shows chaos. So
yes, it does. Yes, it does. Yes, but I'm saying how dynamically you can capture it. Dynamically, it's very difficult because of the small size system. If you go to higher system sizes, people did it in terms of a tensor network with the many higher system sizes, and they have seen this growth. But they have seen like they can extract some of the feature, but in the lower system sizes like L equals to 11, 12, it's still low in the sense, and it's very difficult to see the chaotic feature. So this is one of the way that you can clearly see how this linear growth emerges. Yeah, and to compute this, it takes only a few minutes. This plot to generate the Langdor's coefficients maximum. Yeah.
Hi, can I ask one question? So, can you hear me?
Yes, I can hear you.
Yeah. So this, if OTOC grows exponentially, okay, does it also follow that this Krylov complexity will also grow exponentially?
Okay, that's a good question. There is no statement yet, but there is a conjectured hypothesis, which basically tells you that the Krylov growth, this alpha, this 2 alpha is a upper bound is the Lyapunov exponent. So that means that whenever that is exponential, this should be also exponential. This is a hypothesis in an infinite temperature system, which is proved, but finite temperature system, it is not proved.
Okay.
Okay, so it gives a proper measure of operator growth because it's an easy to compute. Easy means it's quite easy to compute numerically, and it's also defined through the purely quantum mechanically. So you do not need to have any semi-classical picture, but you can apply it to semi-classical picture as well. And the good thing is that any one-dimensional problem, it can be mapped to this tridiagonal form, the simple tridiagonal form, which have a physical intuition.
Pratik?
Yes.
You have 20 more minutes.
Oh,
so just letting you know.
Okay. But then I need to
or maybe 30 minutes maximum. Yeah.
Okay. Sorry. Yeah. So
Pratik, here again, I have a question regarding last slide. You have you're mentioning there is a bound given by the Lyapunov exponent. But what will happen if you have several positive Lyapunov exponent? It is only given by the maximal
Lyapunov. Yes. The bound is for the maximal one. The maximal Lyapunov exponent is upper bounded by the Krylov exponent.
I think you mentioned that, okay, this is very easy to do for small system size. So, I mean, if we look at the static measure of chaos, the Wigner-Dyson statistic that you mentioned, it shows. So that only you can see going to large system size. So how you are relating that, I don't understand. I mean, Wigner-Dyson for...
This one you can also do large system sizes. Yes.
No, I mean, the measure you plot there, let's say 9, 10, 11, 12. So for a comparative of measuring the Wigner-Dyson statistics, so that is small, right? I mean, Wigner-Dyson statistics required you can go up to like 24, 30. I mean, only in the large system size thermodynamic limit you will see that Wigner-Dyson in a good way. So you're saying like, so you're saying this is small system size, this is giving a good measure, but so small system size
even in small systems, it gives you the it gives you the good way to see the chaotic. Large system sizes, of course, I mean, if you go to L equals to 24, you can see a clear linear growth for increasing for very large n, right? So if I compute different n, and I can see there's a clear trend. So from there, I can see that even in the small system sizes, I can have a very good linear growth, which means it's a chaotic feature. And if you do a Wigner Dyson in L equals to 12, is not very large in the sense, right?
Yeah, so
that is what
I was asking, like, the well-established static measure, like the label spacing or something, that ratio. I mean, that will, the small system set, that will not give you a good chaotic measure.
Yes, yeah. I mean, yeah.
So is it like what from you are saying, okay, for small system set, even for L equal to 9, it is chaotic. So is it an artifact of finite size, or I mean, that is a mismatch, like from static to dynamic. So
the Hamiltonian is chaotic is a chaotic. It doesn't depend whether is L is small or large, right? I'm saying the Hamiltonian is chaotic. How do I capture the chaos? Because I have a finite resource of my computational resource. So the easy things to that, if I can devise a quantity that can track this chaos in a very small system sizes. So this is, I'm saying, is a one way that even in the small system sizes, you can see the chaotic features. If you have a many high power of the computer, you can definitely full diagonalize it, doing full computation is perfectly fine.
Okay, but the finite volume effects have been checked for these kind of operators. That's what the question was.
Finite
How
volume?
well are the finite volume effects characterized? Do you know a functional form which characterizes the finite volume effects in these kind of algorithms or these kind of operators? Do you know the functional form, or
Functional
how
form?
much severe it is, or how much the finite volume effects?
Yeah, fine. So the finiteness effects come into this plateau. This is the feature. This is the plateau feature. This is basically the finite size effect, for example.
Yeah,
so
but you're mentioning in OTOC you don't see this linear rise, so that's what the question was. In OTOC also
so
you will
you
see
can
saturation like this.
Okay, so you can compute the saturation of this quantity, for example, up to some saturation, and you can compute with how my system sizes changes the saturation, and it increases linearly. So that means that infinite system sizes, it will only show linear growth because it's basically saturated to infinite. It's only show the linear growth, which is the thermodynamic limit, and that is what is the hypothesis says. The Bn will always show asymptotic linear growth.
So actually, my question is, I suspect that the model is chaotic or non-integrable only in the thermodynamic limit or large system.
No. Even in small size system is chaotic. It's just a Hamiltonian feature. Doesn't depend whether if you take a two-side system, maybe it's an integrable, but after like 3-4 sides, it's a chaotic model. So it's basically the feature of the Hamiltonian. It's not like I have a 50-side Hamiltonian is a chaotic, 20-side Hamiltonian is an integrable. It's basically chaotic Hamiltonian. Any question? Yeah, so I need to go a bit fast, sorry. Yeah. So people used to think that this linear growth, you just compute Langdorf coefficients for the systems, and you see the linear growth, Langdorf coefficients, is a hallmark feature of quantum chaos. But no one asks these questions, whether how universal is this feature. For example, what are the necessary conditions? Suppose if I get a linear growth of a systems, does it mean the system is chaotic or not? Okay. So this is one of the things that results we showed, that the linear growth of Langdorf coefficient does not necessarily imply chaos. So chaos implies your linear growth, but the linear growth does not necessarily imply chaos. For example, one of the example we studied is a called Lipkin-Meshkov-Glick model. It's a quantum optical model, and this model has been solved exactly. So it's an exactly integrable model, and in the semi-classical limit, it has a saddle point in its phase space. So it's so this saddle point, if you compute the Langdorf coefficients in this model for an initial operator, you will see a clear linear growth. which is very unexpected results, because you use an integrable model, you expect a sublinear, not linear growth. But this linear growth comes from this is semi-classical saddle. But once you remove the saddle, you will clearly see that is a feature of integrability. But with the saddle, with the complete Hamiltonian, which is usually known as saddle-dominated scrambling, dn grows linearly. That means your linear growth is Lang's coefficient does not necessarily imply chaos. So the operator growth hypothesis, this hypothesis it's a necessary condition, but not a sufficient condition for chaos, which is okay. So this is one of the counter example that we provided, and after our work, there's a lot of studies that check the hypothesis in some different systems, which is called some anomalous systems. These kind of things happen, but usually in a regular system, your BN and linear growth usually correlated, but not always. So we need to be careful when we define the hypothesis and take the hypothesis in the linear growth. Okay, so this is one of the, and someone is asking that what is the other basis? If I can define another generalized Pauli basis, I can expand everything, compute everything. Yes, you can, of course, compute everything. You can expand the operator in OT in terms of a generalized Pauli basis with some coefficients. However, calculating these coefficients is very, very difficult, because there's no recurrence relation of these coefficients, and you can define a similar notion of complexity or growth. You can define, and this is exactly defined in this paper by Robert Stanford and Susskind, and they exactly computed this complexity for L equals to 8 at max. You cannot compute more than L equals to 8 to see the cure, because it's a very challenging question. However, the one question is that this basis is fixed. You have a generalized Pauli basis, this is a fixed basis. Every time defined operator, it changes this thing quantity. But here, you are changing this operator every time you are choosing a different operator. It's a dynamically generated basis. So there's a cost. There's no free lunch. There's a cost of this ON. Yeah, these ONs, Krylov basis, are slightly more difficult than the generalized Pauli basis. But with these difficulties, we can clearly see that this phi n makes evolving equation 1 is simple. So you can define a Krylov complexity in this way. So this is slightly difficult. So the difficulties goes in this Krylov basis, but the quantity that we are wanting to extract are very simple. So this is a different way to how you want to extract in the Krylov in your operator growth. And the Krylov basis gives a very, very simple way to physically intuitive and computationally efficient way to do this computation. Okay, any question? Okay, if not, then I will next go to a next thing. Topic of this Krylov, how we want to generalize these notions into open quantum systems, because open quantum systems are quite relevant in this era, which is usually called noisy intermediate scale quantum era. And noisy usually means this openness, like a noise, which makes your systems open quantum systems. So the question that we ask is, how does the information flow across a system which is connected to a dissipative environment? And can we quantify some universal quantity for some dissipative information flow? It turns out that before us, these questions have never been asked, because there is no useful formalism to address these questions. But now we have this Krylov formalism, and it is a very intuitive way to generalize this formalism to the open quantum systems. So this open quantum system is basically system plus environment, which goes on an inter-evolution, and you can trace out the system completely. So the system's dynamics is no longer an inter-evolution, is a non-inter-evolution, which is dictated by something called Lindbladian, which is a non-Hermitian operator. Previously, we have a Liouvillean, a tridiagonal Hamiltonian, which is a Hermitian operator. And you can see that this Lindbladian, it's basically written in terms of a complicated form. And the first term is basically the inter-evolution that we have encountered before. They can operate with the commutator with the Hamiltonian. This is the Liouvillean. And there's a second term which destroys the hermiticity property of this Lindbladian. And these are known as the jump operators. A jump operator is basically depends how your system, for example, system and environments are coupled to each other. Okay. So it's how we model your open quantum systems. Different open quantum system you can model differently. So different jump operators, you have a different jump operator. But the message is that you can have a generalized form of this Liouvillean, which is Lindbladian. So once you have a Lindbladian, you can ask that, okay, so can we implement the Krylov space algorithm directly with this Liouvillean? Because this gives a prescription now, because I can generate a Krylov set of basis and I can study the operator growth in these systems by just generalizing these things. The answer is that what you will get is you will get a completely mess. You will not get a correct answer, because the inter-evolution is generated by a Hermitian Liouvillean, but a non-inter-evolution is a non-Hermitian Lindbladian, and the Langdus algorithm fails. You cannot apply the Langdus algorithm because it's suited for the Hermitian evolution. So what you need to do is a kind of generalize the Langdus algorithm that we defined, that we did the Langdus algorithm. It's a well-defined algorithm in computer science tradition. So we imported from the machinery from the computer science algorithm tradition and implement in the setup. So what we do is that instead of one Krylov basis, I create two separate Krylov bases. One evolved by the Lindbladian, one evolved by the conjugate of the Lindbladian. Previously, Lindbladian and the conjugate was same because of the Hermitian evolution. So that's one set. But now we have a two different set. And these two different sets, they are not individually orthonormal. That's because they do not generate a Krylov basis. However, we can impose a condition that these two bases are bi-orthonormal, that the bases they defined, they are individually not orthonormal, but they are bi-orthonormal, the basis. And this is a well-defined machinery people use in, for example, in non-Hermitian quantum mechanics, where you can see that your Hamiltonian, if you have a non-Hermitian Hamiltonian, the eigenbasis is not orthonormal, but you can define a bi-orthonormal eigenbasis. It's a similar in operator space. So in this map, if you follow the same procedure, then you can generalize to the non-Hermitian, what is called non-Hermitian Krylov chain. So you have the same equation, but now you have an extra additional term here, which is basically comes from the non-Hermitian Krylov chain. And here you can map your Lindbladian in this tridiagonal form with a diagonal element. And this is a pictorial representation how your dissipation acts. So each wave function now dissipates. And this wave function is not conserved now because of the dissipation. Their sum will not be, they will not sum up to be the unity. So you need to define Krylov complexity by a normalized Krylov complexity, because this is not one. In the Hermitian cases, this is one. So you have the definition. This is a generalized notion of Krylov complexity, and you can apply to an open quantum system. So once we apply it, so the first thing that you may ask that, okay, I know how these BNs grow asymptotically. This is a hypothesis, operator hypothesis. The question is that how these ANs in a dissipative settings, how these ANs grow, whether they have a universal feature or not. Then I can define a completely generic sense how my operator goes in any quantum systems. Okay, so that we showed in our paper in various spin chains and SYK model by numerically computing and analytically computing. What we show that your BN, this is the previous results, that BN grows linearly, but we also show that AN also grows linearly with a dissipative parameter. This mu is basically is some quantity which is dissipative parameter. Basically, mu is the U here. I should have said U and mu are same. Yeah. So it's a dissipative parameter that, and these coefficients are purely imaginary coefficients, and these are real coefficients. So now you can dictate any operator, any system, whether it's a dissipative systems and non-dissipative systems, you have a very generic notion of operator growth hypothesis. And this, if you have for example, unitary evolution closed system, this mu equals to 0, so it basically reduces back to your simple form. So this is a universal notion of operator growth hypothesis, and you can compute Krylov complexity exactly in this kind of model analytically. And this is one of the results, which is taken from our paper, is that when your dissipation, there's no dissipation, your Krylov complexity grows exponentially. It's a log plot, it's exponential. It's an exponential growth. But whenever you have you put dissipation, you have a dissipation, the growth saturates. And this results is for infinite dimensional systems. So this saturation does not come from the finite size, but it's an infinite dimensional system. And as you increase your dissipation, the saturation value decreases. The one way to interpret why this happens, because this kind of in open system, you can think in terms of like some quantum measurement problem. So suppose is basically how your quantum environment measures your system. The stronger the measurement is, it basically prevents the inter-evolution. That means the lower the saturation value. In these settings, you can define two universal quantity. What is the saturation of the Krylov complexity, and the time scale that it saturates is exponential growth and the saturates. So you can in these settings, you can, for a large class of chaotic systems, this is one of the answer that we have found is that Krylov complexity saturates inversely to the dissipative strength at a time scale which is logarithmically dependent on that time dependence. So alpha is a system parameter. This is a dissipative parameter. So we have checked many examples, many spin chain, and we saw this is a very kind of universal results. So any systems you are supposed to find this kind of results. For example, if U equal to 0, this Krylov complexity, this plateau value is an infinite, basically infinite, because of the infinite size systems, and also this grows to the infinite. Yeah. So this we call the most general operator growth hypothesis, and it's supposedly hold for any system, whether it's a dissipative, non-dissipative, and it's a general statement. Okay. So now I talked about the last thing. How much time I do have? Sorry, wait, no.
Hello. 10 more minutes.
Okay. 10 more minutes. Okay. Thank you. I think it should be okay. So I'll revisit the Krylov state again. So because I'm going to explore something in the quantum state version. So previously, whatever I talked in the quantum operator version, now I talk about a notion, what is quantum state version. So this is the previous slide that I've showed before. And as I said that in the state evolution, you can write your Hamiltonian into this triangular form. And what it means, it's a basis change from your one basis to the another basis. In this case, it's Krylov complexity. You can double state, which is usually people study in the holographic context, because one of the motivation here is now holography. So I'll start with some coherent Gibbs state, some initial state, and this is a typical feature of the Krylov complexity, that it grows initially linearly, then saturates, shows exhibit a peak, and then it saturates to a plateau. This plateau value is an finite dimensional effect, and this peak is a feature of the chaotic system. If you have integrable systems, it does not show any peak; it just goes to saturation. It's similar to the spectral form factor, like it does not show any RAM. So it's a very one-to-one correspondence. So one may ask that, what is the holographic dual of this Krylov complexity if you started the TFD this kind of state? Okay. This is one of the question that has been asked, and to answer this, I will employ a method called saddle point method. So if I again repeat the statement, is that my Hamiltonian is initially a complete randomly written, but I can when I tridiagonalize it basically a tridiagonal basis and the same eigenvalue. So basically a basis change. So there's nothing much changing. So there is a relation between the density of states of the Hamiltonian and the statistics of the Langdorf coefficient, which is we expect. Right? And this is one of the relation which has been shown in this paper very recently, that your mean Langdorf coefficients, this A and B are the mean Langdorf coefficients, because if you have, for example, a random systems, different Hamiltonian, the realization of Hamiltonian will give you a different set of Langdorf coefficients, and you take a mean value of these coefficients. So all are mean. It's also a mean value of a density of states as related to the mean value of Langdorf coefficients here. And X is an index, basically how your Bn n by n is basically how your Langdorf coefficients. So it's like discretizing your index. And you can see that if your density of states is an even function of energy, your AX automatically vanishes here. And this definition actually provides an exploration how your non-perturbative and late time behavior of the non-perturbative behavior of the Langlois coefficients, which is basically giving you the late time behavior of the Krylov complexity. In a boundary theory, it means how your phenomena such as thermalization is encoded. In the bulk, how is your black hole, for example, interior of the black holes grows, this kind of thing. Okay, if you know how the late Langlois coefficients in these cases. So I will give an example in this case in double scale SYK model, which is a version of SYK model where you have a p number of p fermions with the n fermions interacting among each other, and you take a limit where my total number of fermions are infinite and my interaction is also infinite with a fixed this quantity, the scale parameter, and I define as a q is an exponential of e to the power minus lambda. So the large P SYK model is recovered in this lambda equals to 0 or q equals to 1 limit. And this double scale SYK model is also similar to a spin glass model. And one can find the global density of states of the double scale SYK model is exactly in this form, which is shown in the spin glass model in this paper, and then in later paper by Berkuz and collaborators in this paper. There's a lot of studies in the double scale SYK model. So what we want to do, we know the density of states. We want to implement here and try to find what is the Langlois behavior here, because that will give you the late large n Langlois behavior, and which is encoded in the bulk and boundary theory. Okay. So for this, I will implement a random matrix approach. So this is a well-known formula that the density of states is related to the potential, random matrix potential, and this since the density of states are also related to the Langlois coefficients, it is related to the potential as well. For the density of states, double scale SYK model, you can find this potential directly by integrating this principal value integral, which is also an analytically solvable model. And once we impose this constant rho e into here, this formula, and I can solve this equation as a saddle point equation, I get two different saddle point equations. And this saddle point equation can be solved analytically or semi-analytically. And also numerically, one can generate this potential by a Monte Carlo simulation approach and try to see whether to get a good results. And this is what I did in my paper. So numerically generated using this multiple methods, I generated the approach, generated the potential, and then showed how the Langlois coefficients behave. And the saddle point equation, you can see there's a clear match with the saddle point equation for all values of q that I imagine. And this late coefficients, this coefficients is the slope of this coefficients will dictate how your non-perturbative behavior of your boundary theory, and also what it means in the bulk theory. The saturation means that your late time, the interior of the black hole, if it's dual to the double scale SYK model, saturates. So this is an explicit example where you can clearly show that the dual description of my double scale SYK model, the quantity interior growth will saturate. And I extract the functional form of this Pn, and this is basically given by some Q-deform functional form. And this functional form, Q logarithmic functional form, if you expand in a perturbative limit, it will correctly reproduce the wormhole length, which is just shown in our previous paper by Avinovich, Karidosi, Stoner, and they only considered the Langlois coefficients here, this area, which gives you always a linear growth of black hole interior. But here, when you compute this area, you will see the black hole interior growth of saturates. So this gives a clear picture, clear formula for how your boundary theory, the growth of Langlois coefficients behave. And this means that your Krylov complexity defined this way, it produces the wormhole length in this definition. Okay, so I'll just go over this future plans. So for example, in the first case, I provided that first counter example and rule out the sufficient conditions for the operable hypothesis. But what is the necessary conditions of the hypothesis? Can we prove it? And what is the physical mechanism behind the exponential growth of this operator complexity? So this is a very fundamental questions, and we do not know the answer, but possible explanation comes from the free probability theory, which is recently emerged as a novel tools to statistically understand how the dynamics of your quantum systems emerges. For example, in chaotic and systems and ergodic phases, we showed in our research paper that two local operators tend to become statistically independent at late times. That means any correlation, connected correlations, if you compute between these two, they will vanish at zero. So in this framework, you can, instead of P and Q, you can choose any two operator. One could be your initial operator and one could be your timeable operator. So in this case, is a possible direction that whether this statistical independent or freeness is a principal mechanism behind the exponential growth of operator complexity. This is a very difficult question as well, and one of the fundamental questions. So one of the things that it will be a good thing to do I will plan to do in the later by systematically. And the second question, as I said, that we provided a first construction of operator growth and dynamical manifestations of chaos in open quantum systems in this different way. But how do we generalize in beyond Markovian approximation? Because our framework was in a Markovian, where we assume the system and dissipation is a weak interaction. Can we generate to the non-Hermitian systems? We have started an exploration in the settings in terms of a singular value decomposition. So which is basically replacing your framework into instead of the eigenvalues in terms of the singular values. And then another description is that how we interpret this holographically, this dissipation. So in closed systems, it's known that there is a notion called complexity momentum correspondence, which means that rate of change of complexity is a radial momentum of the bulk particle. And this has been proposed by Susskind here, and then very recently it has been shown in the context of Krylov complexity. It is true. It holds. The Krylov complexity provides a natural holographic interpretation in terms of bulk. So it's an interesting problem how to generalize from the dissipative chaos, because the dissipative chaos, we saw that it doesn't grow exponentially, it saturates. So what is the holographic interpretation of the saturation mechanism? Whether some complex metric and other notions kind of things are important in this feature. There's some proposals also called maybe some notion of black holes, some kind of island formalism. You can interpret it in terms of a dissipative chaos. So it is not clear. So we like to explore in this kind of context. And the third problem that is showed that there's a first example of non-portability from a Langdon's coefficients in double scale model, DSS2 model, which is dual to a jetty gravity, but there's no confirmed computation from the jetty gravity side. So I like to perform a jetty gravity computation using this matrix model and jetty gravity correspondence. And there is another notion that how the non-portability Langdon's coefficients give rise to a concrete relation of the higher genus contributions and a wormhole geometries in the bulk path integral, because bulk path integral, whatever I compute is a leading order. Then I have a more subleading term which computes a higher genus contributions. So there is the intuitive way to approach is something that we are exploring at this moment is called Krylov bootstrap, because in this way you can evade all the Langdon's algorithm, everything, by using some self-structure formalism in the Krylov space, and you can devise all the kind of Langdon's coefficients. But this is quite a challenging process. So using the semi-definite algorithms and things. So we are exploring these things, and we want to answer this kind of questions. And we think this is could be one of the fundamental way to do this. Go to the black hole interior using this bootstrap mechanism. So using basically the matrix model bootstrap developed by Lin, because we have a concrete matrix model approach for the double scalar Zwicky model from my first work. So this is what I wanted to say, and thank you very much for your attention.
So I was a little bit interested about knowing more about this non-Hermitian systems that you discussed, open quantum systems.
Yes.
There you gave a very generic statement about whether it is possible to means your Lindbladian can be a bidiagonal and you can always diagonalize it, but it is not always possible to diagonalize or these kind of generalized diagonalization for any non-Hermitian operator. So what are your constraints here? When can you do all of these techniques? So do you have any constraints on which systems you can study versus which you cannot?
So you means here, right?
Yeah.
Yeah.
It's
So
not
here
guaranteed that all non-Hermitian operators you can write it in this way, and you cannot have like a left and right eigenbasis. It's not always guaranteed.
So this is not non-Hermitian operator. This is the non-Hermitian Lindbladian. So
Yeah,
my
that is
operator
fine.
operator is
You are
still
discussing
Hermitian.
it for the non-Hermitian Hamiltonians,
Yes,
and
right,
then you are
right,
yeah.
right.
But then these procedures by Langevin and all, they are not. They depend on what operator you are doing, studying. So it cannot be a very generic statement, I would say. What you made.
This is what is for the local operator, even in, so basically the same closed system, but now I'm interacting with the environment. Same system, I'm not changing the systems. So if you ask for any, like in quantum field theory, how it becomes, that is a complicated question, but the same setup, spin chains, same operator that grows. For example, spin chains. Now, the example that I showed previously, like Langevin growth and saturates. Now I suppose I impose a condition that by end up my spin chain, they have a dissipates to the environment. I can implement the same this formalism perfectly.
Yeah, but the form of dissipative Hamiltonian, even in the spin chain system, are very limited, which you can solve exactly using these kind of algorithms, right?
Yeah, these are all numerically. You can all have to find numerically.
Even numerical also, it is not guaranteed that all any generic non-Hermitian Hamiltonian you can solve.
Any generic non-Hermitian operator is not the okay. So how it is constrained because your Lindbladian operator, so now there comes the physical properties that the Lindbladian evolution, your eigenvalues has to be either complex conjugate in pairs or real. It's a physical constraint, right? Because of the mode of the Liouvillean. And if you impose the condition, you can rule out many possibilities, and you can construct a unique possibilities like this. So you have many possibilities. Yeah.
And then you can constrain what sets of these kind of open quantum systems you can solve for with generic Hamiltonians, right? Because I was puzzled with your statement that it is a very generic. You had these results about this complexity, and this is a very generic statement. But I think
so I'm saying a large class of
one has
chaotic
to have the caveats.
Yeah, a large class of chaotic systems. Yeah, because we have found these examples for a large class, but we haven't proved anything like in statement wise, or we haven't found any counter example yet which doesn't. So we expect that this is a large class of chaotic system it will show.
Yeah,
of course,
but the large class, does it have any symmetry properties? Some things that you can.
Okay. I see what you mean. Okay, so large class belongs to local operator classes, the systems which are all-to-all interacting classes, and systems which the correlation decays at some rate. It is not long range. So this class of systems, so far we have studied, and we showed an universe feature.
Okay. And
so
the second question is, all these techniques that you're discussing, these are all in the context of spin systems.
No, spin, no. I also SYK, all-to-all systems.
Yeah, that is true. But has anything of these been done for quantum field theories?
Quantum field theory, a limited results is known for this case only. This case, for example, this hypothesis, not open quantum system. There's no results for open quantum field theory, because people don't, at this moment we do not know how to implement the Langevin algorithm in field theory. So how do you compute in field theory is basically you start from a 2-point function, and you can map this algorithm to a 2-point function approach, and then you solve the quantum field theory. But in open quantum system, there is
no, even in quantum field theory, not even the open quantum systems, but generic chaotic systems. Has these kind of things have been done?
Yeah, it is partially known.
But
It is
in gauge
partially known.
theories, we know we can, you already discussed at some point of time, you can do some basis decomposition. Means you can divide into subspaces for this, or operator
Right,
spaces
right.
for the Krylov. But in the field theory space also, we know there is separation of different degrees of freedom and generic cases in gauge theories also. So under that assumption, there are studies done already.
Yeah, there are very limited studies.
So what advantage will this Krylov space method give in those techniques? Because there we know how to do those calculations very well.
Yeah, the Krylov in quantum field theory, it's not very well known what is the advantage, but you can actually compute few things, especially the limitation of this how you impose your UV cutoff in quantum field theory. It actually dictates how your Langevin coefficients behave, because this is basically how your, because in quantum field theory, UV cutoff also the IR cutoff. So there are some results for massless field theory, massive field theories, and field theories in spheres and different cases by my collaborator by Demarsky and other people. But it's very limited results, and it is not known whether these Krylov methods are actually, how the Krylov methods are going to actually useful in that context. I mean, not useful, I would say. I'd say like can captures the details of the field theory. It's very open field in the quantum field theory context, also the conformal field theory context.
Okay, thank you.
Any more questions? Yeah.
Complexity for the initial per closed quantum system. So that depends on the operator, right? So there are counter examples that one operator is showing the chaos.
I cannot hear you. Can you repeat? I cannot hear you.
So yeah, so this measure of chaos with the Krylov complexity, just it depends on the what is the initial operator, right?
Yes, right,
So,
right.
So there are counter example who shows that if certain operator is showing the exponential God showing chaos, and if you took another operator, then that might not show that exponential God. So
No, it doesn't. So the hypothesis is that for any local operator, if you choose in the systems, if it is not a very anomalous system, it will show an exponential growth, linear growth of Langevin coefficients for any choice of operator. It just, this alpha will depend on different operator, but asymptotically it will always show linear growth.
But
so it's not that
linear
one
growth,
operator
I mean,
should,
it depends on like the how it's scaling, right? So that I mean, linear means if it just go very slowly, linear and the slope is low, I mean that doesn't measure chaos, right? I mean, as the
linear means this Bn is the hopping amplitude. This means that's the fastest hopping amplitude possible.
Okay.
So that means your operator gets fully delocalized is the fastest way.
Yeah, if I
This
plot that,
the linear, yeah. Otherwise, it's a sublinear, for example. This means the delocalization is slower. This hopping is slower rate, and n is the fastest rate possible. And this linear growth reflects how the Krylov complexity will behave. So if you choose an operator, defined operator, you will still see an exponential growth of Krylov complexity, but with a different exponent. That will differ, but still exponential. Unless you choose an operator which is a conserved quantity or something Hamiltonian, which does not grow. Does this answer?
When you take can you hear me?
Yeah.
So when you take this, operator complexity into open system, you said that you are not going to see the exponential growth of the Krylov complexity, right?
Right.
Okay, but if I take the limit of, open system going to a closed system, right?
Yes.
How does it behave then?
So this is basically, for example, this is the dissipative parameter. It's a very small parameter. You can see this is a saturated.
So then it is exponential.
Yeah. So if it's basically, that means your saturation time scale increases, right? This is the time scale increases. So it will eventually go to the exponential growth at when you just tends to 0. So both the saturation will be approaching the closed system. Also the time scale, the saturation time scale is basically when my deviation start become this. For example, you can compute this is the saturation, where it intersects with the exponential curve. That's my saturation time scale. So it will eventually
So
grow.
here is another, okay, thank you. Here is another comment. Maybe I don't know how effective it will be. So, you can take any open system as a unitary dynamics by appending some ancillary system, right? And this can be done for any time. Okay, from 0 to t, I can deal it as a closed system, unitary dynamic.
Right.
So of course it will increase your dimension, but if you follow the same method that you have done for the closed system, by considering any open system as a closed system with ancillary dynamics, will you get the same result?
Okay, so yeah, so there has been one study which actually did this thing. So if you have an unitary system and you couple to an environment, you have a full knowledge of your system and environment, right? So you can predict, like, so this goes beyond the Markovian regime, because here I do not have any
Markovian,
notion.
non-Markovian, anything,
Anything, yeah. So here I do not have any notion of an purely environment. So I'm just doing a Markovian approximation. I just add in a Lindbladian. So here there is some phase called dissipative phase will not appear in this context, which shows the decay of your complex operator group. But if you consider this kind of unitary plus some system and you compute the full Krylov complexity and then trace out the systems, you will see the 3 different phases. This is the first 2 phase, and there's another phase will come, which is called dissipative phase, which is not visible here because this is a limited case of the one that you just mentioned. So this has been done in one recent paper. Yes.
Okay.
So you gave an example where the Krylov complexity captures chaos, but the OTOC doesn't. Is there an example of the other way around where the OTOC captures the chaos, but Krylov complexity doesn't?
No, not yet. No, is not found yet. So if you found it one thing, then there is also a claim that you can also claim that okay, Krylov is not that good, right? So far it's not been found. So far what you see that Krylov actually has a more information that compared to the photon. But yeah, the example that you're saying is not found yet.
Pratik, I have one thing. Like, let's say if I consider a quantum system where like I have a background field, gauge field. So in that case, will this give you things in a gauge invariant way, like the Krylov complexity? If I introduce a gauge field, a classical gauge field.
Classical gauge field. Yeah, I do not know the answer. Yeah, sorry. So you need to embed your system to the gauge field, right? In that case, suppose, like an interact with the gauge field.
Yeah.
So it becomes sort of open systems.
Yeah, it's not. It's just a background, like we studied Berry phase and all. I mean, Arno
I see what you mean. I see what you mean. I see. There's some studies in the Berry phase context, if I remember correctly. Yeah, but I think I do not have a good answer to your question.
Okay,
Yeah,
fine.
sorry.
Thank you.
Yeah.
Sorry, just wondering one thing, since you said that it is, you showed that it is a, necessary condition, but not sufficient, this linear growth. If I see linear growth, then is it known how I can show that whether it is chaos or not?
Okay, so that is actually an interesting question. So the system that we showed that it is not true. It's a very special class of system. So usually in most of the systems you do not have this kind of anomalies, and even so once you see the linear growth, you can 99% confidently say the system is chaotic. But unless you know beforehand that my system has some anomalies or something, yeah, for this system has an anomaly, we know. That's
so
why.
is there a for sure way of showing whether it's chaos or not? I mean, if I see linear growth, is there something that I check before concluding that it is chaos, or what is it that I would do?
Yeah, so if you have any system and you can study the Krylov complexity, if you see a linear growth, you can first, as a first case, you can see, okay, my system is chaotic.
No, but if I want to be sure, what do I do next? Like in order to be sure.
In order to be sure, the another way to know this for sure is that you need to compute very large late time. So early time they cannot distinguish, but late time they can distinguish, even if you have a system is anomalous. So this system is true for the early time behavior. So if your system is an integrable, but it does not show up in the linear growth, the saturation for the integral system is much lower than the
opposite, right? Early time, your algorithm showed that it is linear growth, but still I'm unsure whether it is chaos or not. Then I need to
so then you need to see the late time. Very late time.
I will ask for late time also whether it's linear. Is that what is the question?
No. Late time is saturates. Let's saturate, and from the saturation value, you can compute and you can tell that the system is integrable or chaotic.
I see.
Yeah. So because but going to the late time is usually numerically challenging. So if you have those
if I see the saturation and then using the saturated value, you're saying I can tell whether it's chaos.
You can clearly tell, but that is a computationally challenging. So we are trying to see in the early time regime. And early time regime, you can do almost all of the cases except few cases which are a bit anomalous. So yeah, that is what I'm saying.
Okay, thank you.
So
thank you. Thanks a lot, Pratik.
Yeah, thank you very much.
Just one question about your future direction. Yeah, right. So you were talking about this dissipative, the chaos in dissipative systems in the holographic setting, right? There is one.
Yes.
Yeah. So what kind of system do you have in mind? For example, the system with evaporating black hole and let's say in ADS, but with non-gravitational path attached or something? Or
yeah. So the first example that I have in mind is like dissipative SOIK model, that the one that I studied. This SOIK model. So what you can do is that SOIK coupled with another SOIK model, and you can study this chaos. So there's a very some recent conjecture that dissipative SOIK gives. So for example, SOIK, which is coupled to another environment, you can model this SOIK coupled to an environment in a two SOIK with a coupling causes a wormhole-like feature. Okay, so it's an equivalent picture. SOIK is a dissipative to the environment is equivalent to two SOIK, which is coupled to a wormhole-like feature. But this wormhole is a bit slightly different than the Maldashana-Chi type of wormhole. So people call it like a Keldysh wormhole because you can describe this in terms of Schwinger-Keldysh formalism. However, this two SOIK now becomes a non-Hermitian SOIK. Non-Hermitian, and in some cases becomes PT-symmetric SOIK. So you need to do a full-fledged of non-Hermitian mechanics to do these settings. So basically what I mean is that in holography interpretation, you can study in terms of some coupled SOIK with a wormhole-like interaction. And this wormhole-like interaction will probably give rise to some sort of holographic.
You're talking about something similar has been done by Sachdev, Subir, I think in this large P limit, the number of Majorana fermions, the P. Okay, maybe okay. This was just a comment, but
that is the usual SOIK model. I'm saying the SOIK model, I have a dissipation to the environment, and that I am modeling equivalently in terms of this Maldashana-Chi type of Hamiltonian, two coupled Hamiltonian with a coupling, and the coupling is basically the dissipative coupling. So the Schwinger-Keldysh equations are same in both equations. It has been recently shown. So it gives like a wormhole-like feature, but not exactly wormhole-like feature. So one is a possible thing that I think people are trying to do this, like how you take this double trace deformation and things for this wormhole-like feature to coupled SYK and becomes an open quantum system.
Okay, anybody in the online? I think no. Okay, thank you, Pratik. Thanks a lot.
Thank you very much. Thank you very much. Shall I leave then?
Yeah.
Okay. Okay. Thank you very much. I look forward